We're going to look at latent heat. So the definition of latent heat is the energy required to change the state of 1 kilogram of a substance. Now, that on its own is not that useful. We can add a bit more detail, which is the detail we require. We can talk about the energy required to change 1 kilogram of liquid to solid, in which case we're talking about fusion. Or we could talk about the latent heat of vaporization, where we're talking about liquid to gas. So students need to know two latent heats, the latent heat of fusion and vaporization. And we should at all times be linking it to this diagram where we're thinking about temperature. And this axis isn't always labeled, but I guess it'll be time when we're heating a substance up. And the graph looks a bit like this. And students will have seen this in year 9 and possibly also in year 7 and 8 as well. So we've got these parts here where we're heating. So we're just heating a liquid. Here we're heating a solid down there, heating a liquid here and heating a gas. And then in these parts here, we've got a state change. And here we're obviously going liquid to gas. And here we're going solid to liquid. And then we can link this back, or we should be linking this back to the idea that in these sections where we're heating, the equation for heat capacity applies, which is equals mc delta T, or it could be Q equals mc delta theta. But for the state change, we're looking at latent heat, and therefore this new idea, the energy required to change the state of 1 kilogram of a substance. So if we want to bring a formula in, we can say that the energy required for a state change is the mass times the latent heat, and then we would add of fusion or of vaporization, depending on which state change we're looking at. So in simple terms, E equals ml, and if we want to look at the units, joules equals kilograms times by joules per kilogram. And it is always worth looking at the units, because this is one of the examples where students can cheat. And I'm going to put cheat in inverted commas because obviously they're not really cheating, but they can look at the units and they can use the units to work out the definition. And students really love it when they think they can cheat. They can cheat with density. They can use the formula, the units for density, which are always given on the answer line, to remember the formula. So here you can say, well, the units for latent heat are joules per kilogram. So what does this mean? It's energy per kilogram for a state change. And if you look at this graph here, you'll notice that this line here from solid to liquid is shorter than the state change from liquid to gas. Why is that? And this is important. That's because if we're going from a solid to a liquid, we aren't really changing much. Okay. Yes, we're breaking some bonds. And because we're breaking bonds, okay, the temperature stays constant, which is, of course, a basic fact that students will know. When we're going from liquid to gas, right, what's happened now? We've actually had a massive change, right? The molecules have barely moved position here, although we have broken bonds here. We've got a large change, and so we need a large amount of energy to really separate these, a huge amount, and to give them the large velocities that they require to be completely free. So this state change here needs far more energy than this state change here, which is a little bit of energy. So we can look at some actual examples here to really see this. We can look at water. So the latent heat of fusion of water is 334,000 joules per kilogram. And for vaporization, it's a massive 2,300,000 joules per kilogram. So 10 times more almost than fusion. And that's fairly common. The vaporization values will be a large amount, typically 10 times more than the value for fusion. So when we're answering questions, a lot of the basic ones are just plug in the numbers into this formula or rearrange it. So you should do lots of practice of that. But I would encourage you, when you introduce it, to think about kind of this kind of approach, where if you had 1 kilogram, how much energy would we require to change the state? If we're going from, say, solid to liquid, we would need this amount. Supposing we had 2 kilograms, okay, that's just the same as saying 2 lots of 1 kilogram, so that's going to be 2 times this amount. Okay, and then you can probably see where I'm going here. We can scale this up. So let's go for 1, 2, 3, 4, 5, 6 kilograms. Let's go for 6.5 kilograms. Okay, so now by this approach of scaling up, we can do 6.5 times by the latent heat to work out the energy required to change 6.5 kilograms. Now, this approach is useful because students do, for some reason, I've noticed, find this concept a little bit hard of latent heat. So it's worth really basic questions, get them harder, and then you can go on to give them any values for mass, for example. Harder questions are going to require two steps, maybe 3 steps, if we're looking at higher tier. So they will typically say something like work out the energy required, but step 1 will be working out the energy, which could be maybe power times time. All right, they might be given a power of an appliance and the time it's on, or they might be given some information relating to electricity. So depending on what stage of the year you're at, you might need to use this idea where we're using current times potential difference times time to work out the energy required. And then perhaps step 2 is energy divided by mass, is latent heat, for example. These two here, where we're combining these two, tends to be the most common ones that I've seen. And they typically are 5-mark questions on a higher paper. The last thing that's worth looking at is 2 demonstrations that you can do. There's no required practical for latent heat, but there's 2 nice demonstrations which you can do to work out the latent heat. So demonstration number 1 is you can get yourself a kettle, and you can put the kettle on a mass balance, and you can turn it on so that it boils, and you can measure the mass before and the mass after. You can use the power rating of the kettle and a stopwatch to work out the energy that's going in, energy power times time, and then you can use the energy that you've put in divided by this mass change. So mass before minus mass after. And that will give you a value for the latent heat of fusion of water. It's a pretty rubbish value. You don't typically get very close, but it's a nice demonstration, and you can talk about why obviously the values are different. The second one that is worth doing is you can get yourself a funnel, a glass funnel, and an empty beaker, and you can put some ice in it, and you can get yourself a heater, and then you can put the heater on. You can melt some water. The water will drip through into the beaker, and again you can put the beaker on a mass balance, and you can work out the latent heat of fusion of water by looking at the current times the voltage times the time divided by the mass change. from the water that's dripped in here, because that's the state change. Now, this again is not going to give you a great value. There's lots of reasons why it won't. There's loads of heat that's going into from the room into this. So you can then talk about the need for a control beaker. This is really good for students to think about. So you set up the same experiment and you also put a heater in, but the heater, importantly, is off. So you don't have the heater on. And then you can look at the mass of water that would melt anyway due to the room. So you can explain the idea of a control. The other problems with this is there's loads of air gaps, which the air is getting heated rather than the ice. So you can crush the ice is one idea. The other typical problem is you'll typically find the heaters stick out and a load of heat is wasted. But these are all really good things because you can test the students' practical skills of improvements. Like I said, it's not a required practical, but it's nice doing as a demo. It's nice to talk about practical skills, and it's nice that students can represent these because there's no reason these couldn't be given in an exam as sort of a data question or a practical themed question.